If you drop a spoonful of table salt into water, you can watch it vanish as it dissolves completely. But not every salt behaves that way. Some dissolve just a little, so little that you might not even notice it happening. An example is lead sulfate. Even though it looks like nothing is happening, enough may dissolve to put dangerous amounts of lead in the water. To predict when and how much of a salt will dissolve, we can use the solubility product constant, KSP, a powerful tool for calculating solubility. But how do we use it, and what does it really tell us? This is Real Chem. Qualitative reasoning can be powerful. When one thing increases, another often does too. But sometimes we have to be careful when making such comparisons. This is the case when we use KSP values to compare solubilities. A direct comparison of KSP values only works when the salts we're comparing have the same stoichiometries. If two salts produce the same number of cations and anions when they dissolve, we can confidently say that the salt with the larger KSP value is more soluble. But when we compare two salts that differ in the number of ions they produce, we can no longer make a direct comparison. KSP alone doesn't tell the whole story. Let's dig in and see why. Some solids, like table salt, readily dissolve in water, while others, like a bar of platinum, don't dissolve at all. Slightly soluble salts lie somewhere in between. They dissolve just enough for a small amount to enter solution, while most remain solid at the bottom. To quantify how much dissolves, we use the solubility product constant, KSP. This is an equilibrium constant, just like the ones we've seen before, but specifically for dissolution reactions, where the solid salt is the reactant and the dissolved ions are the products. Since equilibrium constants describe the balance between reactants and products, a larger KSP means that more salt dissolves. But we have to be careful when comparing different salts. To see why, let's start by comparing iron 3 phosphate with aluminum phosphate. In this comparison, each formula unit of these salts produces one cation and one anion when it dissolves. That means if the solubility of the salt is S moles per liter, the concentrations of both ions are also S. Now, let's use KSP to determine solubility. Since this is an equilibrium, we can write an expression for the reaction quotient, Q. Because solids don't appear in equilibrium expressions, we only include the dissolved ions. From this, we can set up the KSP expression for solubility. Substituting S for both concentrations, we get the following. This allows us to solve for S, the solubility. We find aluminum phosphate is more soluble. From the KSP values, we could have directly ranked the solubilities of iron and aluminum phosphate. Since aluminum phosphate has a larger KSP, we could have confidently predicted that it's more soluble without even doing the full calculation. So simple, right? Well, now let's consider lead phosphate. Its KSP is much smaller than that of either iron or aluminum phosphate. Based on that alone, you might expect it to be less soluble. Here's the dissolution reaction for lead phosphate. Unlike iron phosphate and aluminum phosphate, this reaction doesn't produce ions in a 1-to-1 ratio. And this changes our calculations in two key ways. First, the ion concentration depends on the reaction coefficients. If S moles per liter of lead phosphate dissolves, it produces 3 S moles per liter of lead ions and 2 S moles per liter of phosphate ions. Second, the KSP expression must account for these coefficients. The lead concentration is raised to the third power, and the phosphate concentration is raised to the second power. Substituting these values into our KSP expression gives 108 times S to the fifth power. That's very different from the S squared we found for iron and aluminum phosphate, and it explains why comparing KSP values alone doesn't work when stoichiometry differs. It's exactly why comparing the KSP of lead phosphate to that of iron or aluminum phosphate doesn't give the full picture. Solving for S, we find that lead phosphate actually dissolves more than either iron or aluminum phosphate, even though its KSP is much smaller. So, while comparing KSP values works when salts have the same stoichiometry, it doesn't when the number of ions differs. The actual solubility ranking might be very different from what KSP alone suggests. So when it comes to comparing solubility, KSP is a powerful tool, but only when used in the right context. If two salts dissolve in the same way, their KSP values provide a straightforward comparison, But when the stoichiometries differ, things get more complicated. A smaller KSP doesn't always mean lower solubility. By understanding how KSP and stoichiometry work together, we can make better predictions about solubility and about what's really happening when a solid dissolves.